Okay guys, thought I would pop on, show my face. It's been a while. We are about halfway through Unit 2. So Unit 2 is all focusing on polynomial equations and inequalities. We've basically spent the first 4 lessons, plus our bonus lesson of our factoring review, learning how to factor these types of equations with degrees higher than 2 using things like our remainder theorem, our factor theorem, our zero integral theorem. And so now we're actually going to look at solving the equation. So we'll review what it means to solve a function equation. You guys have solved quadratic equations. You've solved lots of function equations before, but we'll just review what that term means. What does it mean to solve an equation? And then we'll just do some examples. Really, it's just tying together everything that we've been doing so far in this unit. So, Unit 2, Lesson 5, I can use the factor theorem and long division to factor polynomial equations higher than degree 2. And I can determine the solutions of a polynomial function using the factors. And I can use technology to check my work. Okay, so 3 different things going on here. We've already done the first one. We've already been factoring polynomial equations higher than degree 2. And now we are taking those factors and just stating our solutions. So what does it mean to solve a polynomial equation? What is a solution? For example, why you would have learned this in grade 10, again in grade 11, where we say, okay, solve the following, and you go, okay, well, I've got to take 2x squared minus 4x minus 30, and I got to set it equal to 0. And I just like to be clear here because oftentimes I will get students in grade 12, and they're going through this motion based on nothing other than memorizing steps. Why? I like to understand why are we setting equal to 0, and what does it mean to solve. So when we do set it equal to 0, what that means is we want to know when will this function equal 0? Or in other words, what value or values of x, when subbed in, would result in this entire function equaling 0, or having a function value of 0. This here is f at x. F at x is defined as this function. What values of x are going to make that function equal 0? And then I want you to think about why we care about that. What does it mean if we take a function, and let's just quickly draw a sketch here of some quadratic. As you guys know, they're never pretty. But the times where this function has a function value of 0. Remember that we used to call this axis y, and we can still call it our y-axis, but it's also our f at x axis, and this is our x-axis. When we have an f at x value of 0, that's here, right? This is f at x equals 0. So the times where this function has a function value of 0 are here and here. So when we set it equal to 0, we are solving. We want to know when will this function, for what values of x, have a function value of 0. And those points on our graph are our x-intercepts. Okay? But we also call them our roots. And we also call them our zeros. And we can also call them our solutions. So lots of synonyms. So when it says solve the following, it's really asking you to find the x-intercepts. All right? Unless it's not equal to 0. It might be, well, when is 2x squared minus 4x minus 30, when is it equal to 2? And now we're interested in these x values that correspond with a function value of 2. But we'll look at some examples where we're not setting it equal to 0. Okay, so just to quickly go through, like if this was an example, we would common factor first. We've got to pull that 2 out. So we'd have x squared minus 2x minus 15. This is a simple trinomial as far as I can see. A value is 1. So if I want to figure out 2 numbers that add to negative 2 multiply to 15, the only numbers that multiply to 15 are either 3 and 5 or 1 and 15. And so right away, these can have some difference of 2. So I'm going to go, okay, I know that it's going to be a 3, and I know it's going to be a 5, and I know that one of them has to be a negative because they multiply to a negative. So which one? Well, the 5 would have to be negative because negative 5 plus 3 would result in this negative 2. So there we have factored it. And to solve, if we said, okay, solve for when f at x is equal to 0, we want to know when would this function, so if we sketch it, it has an intercept at positive 5, it has an intercept at negative 3, it is opening up because the leading coefficient is positive, so we could solve in further to determine the y-intercept or the axis of symmetry or something, but not pretty, as we know. You guys get the point. There is our solutions, though. Okay, so our solutions, therefore, solutions are x equals negative 3 and 5. These are our factors. These are the corresponding solutions. And to get the solutions, we set the factors equal to 0, okay? And we've already talked about this in a previous lesson, but again, the reason that this positive 3 yields a solution of negative 3 is because we want to know what would I have to sub in for x to make this factor equal 0, because if this factor becomes 0, the whole function will have a value of 0, because the operation between these is multiplication. This is 2 times x plus 3 times x minus 5. And what we know about multiplying by 0 is anything multiplied by 0 is 0. So as soon as this factor becomes 0, the whole function has a function value, a y value of 0. And then we rearrange to isolate x. And we do the same thing here. Okay, so just remember, these are factors, these are solutions. Solutions come from setting factors equal to 0. So solving polynomials is easy if you're given it in factored form. Determine the solutions for the following polynomial equation. 2x times x plus 3 times 3x minus 4 times x minus 7 is equal to 0. In other words, when is this function equal to or has a function value of 0? And at this point, we're just doing, like I said, we're taking the factors, and this is a factor. This is a stretch, a vertical stretch. There is no x here, so it's not a factor. This is a factor. It has an x. So when will 2x equal 0? Because if this factor becomes 0, the whole thing is, well, we can isolate, but it's just going to be when x is equal to 0. When will this factor equal 0? When will x plus 3 equal 0? So again, we isolate, but we get x equals negative 3. Now, this one's a little bit different. We want to know, when will 3x minus 4 equal 0? So I'm going to write out the steps for this one. Opposite operations to isolate x. Okay, so I want to get rid of this negative 4, so I add 4 to both sides. I have 3x equals positive 4. Want to get rid of this 3, so I divide both sides by 3, and I end up with x equals 4 over 3. That is the solution. If you were to convert this to a decimal, if we have 4/3, then we have 1. We could write it like this, 1.333 or 1 1/3. But if you are, we would just leave it as this fraction, because then we get into rounding. If we were we could, and this would be helpful for graphing, but this is the solution I'm looking for. Leave your solutions in as fractions, and then when will x minus 7 equal 0? We add 7 to both sides, and we get x equals 7. So, therefore, solutions are, and it doesn't really matter, but I would always try to write your solutions from left to right. So we have a negative 3. That's this one. We have a 0. That's this one. We have a positive 4/3. And we have a positive 7. Okay? Now that is super duper easy when we are given the polynomial in factored form. What about equations that are not in factored form? Okay, so our equations that are in standard form. We do have some tools. We have graphing calculators, and we are going to use those to check our work, but you need to know how to solve polynomials without a graphing calculator, which means you have to know how to factor. Okay, we have to be able to go from standard form to factored form by factoring. Once they're in factored form, we already know that determining the solutions is easy. We've been doing this since Unit 1 when we were drawing sketches of polynomial functions from factored form. So we have to factor, but how? How do we factor? Well, we use the integral zero theorem to determine some possible factors. Then we use the factor theorem to confirm one factor, which is also using our remainder theorem because we're looking for that remainder of 0, which is by definition our factor theorem. Once we find one factor, we use long or synthetic division to divide out that factor. You'll be left with a quotient that is of one less degree. So if you were originally factoring a degree 3 polynomial, you'll be left with a degree 2 polynomial. If you were originally factoring a degree 4 polynomial, you'll be left with a degree 3. The reason is you're only ever factoring out one factor is always going to be linear. You're only ever factoring out one degree at a time. You will repeat these steps until the quotient that you are left with is degree 2. So if you are originally factoring a degree 3 polynomial, you find one factor, you factor it out, you're going to be left with a quotient that's degree 2. That's great, you're done. You don't have to go back to these steps. At that point, you will use familiar methods that you already know for factoring a quadratic to factor the remaining quotient further. A lot of words, but let's just look at an example. Okay, so solve the following. When will 2x cubed minus 3x squared minus 5x plus 6 equal 0? We want to know when will this function have a function value of 0. Remember our integral zero theorem. If this was all in factored form, like this one is, our c value is going to come from multiplying our numbers, our constants. Okay, so the factors are going to be multiples of 6, or there's going to be at least one that's multiple of 6. So our possible factors are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. It doesn't save you a ton of time, but at least we know that if we're really struggling and we don't find a factor in 1, 2, or 3, we're not going to mess around with 4 or 5. We're going to go right to 6. So I just recommend that we always start with 1 for 2 reasons. It's the easiest one. If we sub in 1, nothing changes, right? 1 cubed times 2 is just 2. 1 squared times negative 3 is just negative 3. 5 times 1. So when I say nothing changes, it's so simple to figure out what it will be, because it will just be 2 minus 3 minus 5 plus 6. This would just be 1, this would just be 1, this would just be 1. 2 minus 3 is negative 5. Negative 5 minus 5 is negative 10. Negative 10 plus 6 is negative 4. That's no good. Okay, so we're going to have to keep going. We're going to have to move on to something else. So let's see, what about if we sub in a negative 1? Oh, sorry, one sec. Someone's knocking on my door. Okay, sorry guys, someone was knocking at my door, but it's a good thing they did, because then I realized it's Monday, made a mistake here. So let's get rid of this. 2 minus 3 is not negative 5, in case you were wondering. I'm sure you guys are watching this and you're like, yeah, we know. We already caught that. So, okay, 2 minus 3 is negative 1, and again, just to show you that we're all human. So negative 1 minus 5 is negative 6. Plus 6 is, in fact, 0. Yay, that's great, because the less times we have to do this, the better. So what we have confirmed that x equals 1 is a solution, meaning if we were looking at a graph, at this point here, the function would equal 0. So that means that therefore, x minus 1 is a factor. Okay, so remember that the factor has to be the opposite. We would have to isolate this to figure out when does x equal 1. We want it to be 0, so we would move it to the other side, so it would be x minus 1. Okay, so just be really careful. When you get this number here, that is the solution. We have to adjust for the factor. All right, so we have used our factor theorem to confirm one factor. Now we will use synthetic or long division to divide out this factor. So this is step 1. Step 2. Now, when you use synthetic division, the number that goes on the outside is the solution not the factor. So it's a 1 over here. And then I have a 2, a negative 3. And I always want to make sure I have all descending power. So I have power 3, power of 2, power of 1, power of 0. So that's all good. So I've got 2, negative 3, negative 5, and 6. This is a little overkill over here. We'll save ourselves some space. So I got to bring this 2 down. 1 times 2 is 2. I'm adding negative 3 plus 2, negative 1. 1 times negative 1 is negative 1. Negative 5 plus 1 more negative is negative 6. 1 times negative 6 is negative 6. 6 plus 6 negatives is 0, which is great because this is my remainder. And we need our remainder to be 0, otherwise 1 is actually not a solution. So now, what we've confirmed, again off to the side, maybe I'll use a different color. This is our function here. What we know so far is that 2x cubed minus 3x squared minus 5x plus 6 is equal to x minus 1 times 2x squared minus x minus 6. Okay, so I've factored a little bit out here. Like we said, because we're factoring out a degree 1 from a degree 3, the quotient, this is our quotient that we're left with, is a degree 2. And at this point, we're going to stop. We're not going to use our factor theorem long division. We could, but we should be pretty confident in our methods of factoring degree 2 polynomials at this point. So our next step is now factor this degree 2. So to factor this, I'm looking at it, a is not 1, so it's not a simple trinomial. I can't make a 1 by factoring it out because I can't factor out a 2 here. It's not a difference of squares. There's 3 terms. It's not a perfect square trinomial. 2 is not a square number. I'm really left with no choice. I have a complex trinomial, so I can try and use those methods, and if not, I can use the quadratic formula. So I'm going to use let's use the t method here, because we do have decomposition. So I'm going to set up my t table. So I've got 2 times 1 and 1 times 2 on this side. And those are the numbers that can multiply to a. And on the right side, I have the numbers that can multiply to 6. So I have 1 times 6 and 2 times 3. I only have to write the reverse for one side of the table. So if I only put 2 times 1 on this side, I would have had to do 1 times 6, 6 times 1, 2 times 3, and 3 times 2. So the number that has the fewer multiples is definitely the number you want to consider both options. So I'm going to do 2 times 3, which is 6, and 1 times 2, which is 2. 6 and 2 cannot give me a 1. So now I'm going to do 2 times 6, which is 12, and 1 times 1, which is 1. 12 and 1 cannot be combined to give me a 1. So I'm going to move to this one here. I've got 1 times 3 is 3, and 2 times 2 is 4. 4 and 3 can definitely be combined to give me a 1. So I'm going to be dealing with these two numbers and with these two numbers. So when I do that cross multiplication, I have 2 times 2 is 4. I have 1 times 3 is 3. Those can give me a difference or a sum of 1. So my factors would be something to do with 1x and 2 and 2x and 3. And then I got to figure out what my signs are. So these things 2 and 3 need to multiply to give me a negative 6. So first off, I know one of them is a negative. These two numbers are where my 4x comes from. And these two numbers are where my 3x comes from. So it's helpful to consider which of these needs to be positive and which needs to be negative. The 4 needs to be negative, the 3 needs to be positive. Negative 4x plus 3x will give us negative 1x. To make this 4x negative, this needs to be negative, and to keep that 3x positive, this needs to be a positive. All right, so now what we know is that the factors, okay, so let's go over here. And this is not the solutions, but factors are, and don't forget about the ones we've already done, okay? We already factored out that x minus 1. Factors are x minus 1, x minus 2, which is this, 1x minus 2, and 2x plus 3. Okay? Those are the factors. That is not what the question asked us. Solve. To solve means to find the solutions. Therefore, and we could go ahead and say, okay, well, the solution here is x equals 1, and the solution here is x equals 2. And again, if you're not feeling confident, then you can write out your steps and say, okay, when does 2x plus 3 equal 0? When 2x is equal to negative 3, when x is equal to negative 3 halves. So therefore, solutions are x equals negative 3 halves, positive 1, and positive 2. Okay, so that's a lot of work, guys, just to get to the solutions. Let's just do a quick check. So 2x cubed minus 3x squared minus 5x plus 6. So we've got 2x cubed minus 3x squared minus 5x plus 6. There's our function. We could call it f at x, but we don't really need to. And let's check if our work was right. We have one solution at negative 1.5, which is negative 3 over 2. We have one solution at 1, positive 1, and one solution at positive 2. So this is how you can check your work using Desmos. Obviously, it's very, very easy because you just put your function in and you're just looking at your x-intercepts. If you touch anywhere on your function, the x-intercepts will automatically appear as points of interest, so you know the exact value. But a lot of work to get there. All right, do we need to do? Yeah, we need to do. Okay, so let's take a look at this example here, just to show you the different ways that you might see these questions communicated. So x to the power 4 minus x to the power 3 plus 41x is equal to 21x squared plus 20. So when we are looking at this, really what we're doing is we're trying to figure out when does this function equal this function? When do these functions have the exact same function value? In other words, what is their point of intersection? We could definitely do this on Desmos. We could put these two functions in as two separate functions, and then we could solve them. But again, that's not the method we're going to be using when we're solving by hand. So what we need to do, and what we know how to do, is solve when it's equal to 0. So when we bring these all over here and turn it into one function, so if we say, okay, I've got x to the power 4 minus x to the power 3 plus 41x, if I want to bring this or get rid of it on this side, then I have to take away 21x squared from both sides and take away 20 from both sides so that I'm left with 0. Then I want to clean this up and write it in descending form. So I have x to the power 4 minus x to the power 3 minus 21x squared plus 41x minus 20 is equal to 0. Now when I solve this polynomial function, this degree 4 polynomial function, because I've rearranged, I've not changed the question, the solutions to this function will be the point of intersection of these two functions. So anytime you're asked to solve, and this should say, solve the following polynomial equation, right? It's still an equation. The method is always going to be isolate the one side of the equal sign to be 0, okay? So now we go back, we use those steps, use our integral 0 theorem, use our factor theorem, so on and so forth. Our C value is 20, so we have a lot of possible factors. We have plus or minus 1, plus or minus 4, plus or minus 5, plus or minus, 2, plus or minus 10, plus or minus 2, and plus or minus 20. So any of those would be a good starting point, but to make our lives easier, we will begin with 1. What happens if we sub in 1? Well, this becomes 1 minus 1, right? 1 minus 1 minus 21 plus 41 minus 20. And 1 minus 1 is 0. Minus 21 is negative 21. Okay, we can write from there if we want. Negative 21 plus 41 minus 20. Negative 21 plus 41 brings us up to positive 20, and then we take away 20, and we're left with 0. So I will try to be kind and make That first one often within reach, within the first, within one or two. But if you're dealing with textbooks questions, you just never know what you're going to get. So what we've confirmed is we know that therefore x minus 1 is a factor and x equals 1 is a solution. So we're going to use long division. Okay, so this is step 1, and this is step 2. We're going to put the positive 1 over here, and we have to get all of our coefficients. So we have a positive 1, a negative 1, a positive, sorry, that's out of order. Oh, positive 1, negative 1. We're looking at this one here. Negative 21, positive 41, negative 20. Bring this down. 1 times 1 is 1. Negative 1 plus 1 is 0. 1 times 0 is 0. Negative 21 plus 0 is negative 21. 1 times negative 21 is negative 21. 41 plus 21 negatives is positive 20. 1 times positive 20 is 20. Negative 20 plus 20 is 0, which is great. That's our remainder. We know that this is in fact a factor. So what we know so far is that x minus 1 times x cubed, it's only 1 degree less than the original function. This was degree 4, so that's how I know this is x cubed. There is no x squared term, so I'm going straight to minus 21x plus 20, okay, are factors. And we now need to factor this to find more solutions. So we now have a degree 3. Unless I believe this is a difference of or sum of cubes, I'm forced to go back to that same method, sub something in, check if it equals 0, so on, so forth. So let's check. Let's try 1 again. I would always start there. F at 1, we're looking at this function, is going to be 1 minus 21 plus 20, which is actually equal to 0, which is wonderful because now we know that 1 is a double or an order 2 root of this function. We still have to divide it out from here, so we're still going to use our synthetic division and put 1 over here. But now we're looking at these coefficients, which are these ones here. So we have 1, 0, negative 21, and 20. And we bring our 1 down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 21 plus 1 is negative 20. 1 times negative 20 is negative 20. 20 plus negative 20 is 0, which is brilliant. So now what we know is x minus 1 was a factor. X minus 1 was a factor again. We factored that out, and we're left with x squared plus x minus 20. This is really neat because two things. We can now write this as x minus 1 squared times x squared plus x minus 20. Because if we were factoring this with the intention of sketching it, we would need to know the order of each factor. And often the examples that we've looked at, it's order 1, but that's not always the case. Sometimes we actually factor out. So a good lesson here is if you've already subbed in a 1, it doesn't mean you can't sub in a 1 again when you're dealing with a new polynomial. So here we've got x minus 1 to the power of 2, and now we need to solve this. This is a, as far as I can tell, simple trinomial. A value is 1. I need two numbers that add to positive 1 multiplied to negative 20, and that's going to be 4 and 5. So I've got x minus 1 squared. I'm going to have a 4, and I'm going to have a 5. And because that 20 is negative, one of these has to be a negative. And so I need to have, if I did negative 4 plus 5, that would bring me up to positive 1. So what we've done is factor. So far we have factored this polynomial, Now we need to make sure we state our solutions. Okay, so it's a degree 4 polynomial. Does not mean it has 4 solutions. A degree 4 polynomial can cross the axis as little as 0 times because it's an even degree. So then now we would say there is a solution at x equals 1. This is not, we're not taking the square root or anything. This just tells us the behavior of the function at x equals 1. It's going to have that quadratic behavior. It's going to touch the axis. This one here is a solution at positive 4, and this one here is a solution at negative 5. So therefore, solutions are x equals negative 5, positive 1, and positive 4. A lot of work for one question. Okay, this video is getting long. If you're like, yeah, I get it, I've got the point of this, you may wish to jump right to your practice questions. Disregard this. This is for my in-person class. But you may jump to the practice. But I'm going to start another video where I look at some special cases and just give a little more instruction on that, as well as really what we do is we take those solutions and go one step further and actually draw the graph. So we review things like what's the degree of the polynomial, what's the leading coefficient, how do I factor, get the solutions, and then sketch that polynomial. Okay, so choice is yours if you want to view the second video.